All right, going back to forces, we take a look at this diagram. Now this object is falling, but what force is not happening in here? Yeah, there's no air resistance. So again, in AP Physics, we tend to ignore air resistance. If we're in the classroom and we're shooting marbles, it is pretty small value of air resistance that would even happen on that. But if we were outside, and depending on the object that's flying through the air, we would have to take air resistance into consideration. We just don't do a lot of that stuff in the classroom. All right, so from last time, what we need to do, remember, is we're going to draw a circle around our object. Okay, so we want to make sure only the forces that we're talking about are working on the object. And what's happening here? What force do we have? Gravity. The force due to gravity. Good job. And so if we drew a free body diagram on the AP exam, they just want you to draw that guy, call it a day. Okay. So here's the thing. Let's say you guys were skydiving, right? You jump off of a plane, all right, and you're headed toward the ground. Are you going to keep accelerating all the way until you hit the ground?
No.
No, right? But why? Right, because air resistance. But let's talk about this for a second. You have air resistance, so you jump off the plane. What is happening to air resistance as you're getting faster and faster? It increases, right? But it's not going to increase forever. What's going to happen is at some point, the air resistance, if we drew it as a vector, it's actually going to equal that force due to gravity. So the force from the air resistance is going to equal the force due to gravity. We call that a drag force, okay? So we're falling through the air. They end up equaling each other. Now, if your net forces then are equal to 0, shouldn't you be stopped? No, exactly. Right? We're going to be in motion, right? If you're falling through the air, you're in motion. So what does that mean? If your net force is 0 and you're in motion, what does that mean about the motion of you as you're flying through the air once they're equal? It's constant motion, which means what about our acceleration? Acceleration is 0, okay? So this is a big idea, and you guys are going to hear it over and over again. If your net force is 0, two things are happening. You're either at rest, okay, so your object is not in motion, or your object is moving with constant speed. So once you guys are in the air, right, and you reach that velocity, that we call it terminal velocity. Once you reach a terminal velocity, it means that your air resistance force equals your gravitational force. And so you're in motion, constant speed, but your net force is 0. So every time you hear net force is 0, don't just automatically say, oh, you're at rest. You need to remember you can be in motion, but it's constant velocity. All right, number 7. Okay, when we draw the circle, where are we going to draw it around? Just the box. Now this is important because we have other forces occurring in the diagram. So when we're trying to draw a force diagram, a free body diagram, we want to make sure to isolate the object that we're trying to identify the forces of. So when you look at this, what are the forces? We have gravity, good. And we have tension, excellent. Okay, we actually know more information about this. So let's read through. Everybody take a second, read through the description. Okay, why is that important? Yeah. Because we know that acceleration is 0. If acceleration is 0, what do we know about the net force? That has to be 0. And if the net force is 0, what else do we know? We know that the force due to tension has to be equal to the gravitational force. So when we add those together, because they're equal and opposite, when we add these two forces, they would equal 0. So the sum of the forces is 0. So these two have to equal. If we draw the free body diagram, That's what it's going to look like. Would we put congruent signs on the free body diagram? For the AP exam, no. But if we were trying to set up an equation, we would draw a separate one, and then we can put that on there. But for the free body diagram, if that's all the question is asking, we don't want to draw any congruent symbols, any component vectors. We're going to leave that as is. Okay, so number 8, we have this ball rising in a parabolic path, but this time what do we have? We do have air resistance. Okay, so how many forces are working on this ball then? 2. Why would you think 3 though? We have gravity, right? The force due to gravity. How would we draw? It's called a drag force. So air resistance is a drag force. How would we draw that on here? All right, so one suggestion is perpendicular to gravity. So let's take a look. If we had this, drew the same ball, perpendicular to gravity would be here. Do you guys think that would be the air resistance here though? What is air resistance similar to for other objects in motion? There's another force that's very similar. Someone I think mumbled it. Yeah, it's very similar to friction. And what do we know about friction forces? It's the opposite direction of the motion of the object. Excellent. Okay. If it's the opposite direction of the object in motion, we have a problem for this. What is the difficulty of drawing it here? It's a parabolic path, okay? So we can certainly draw right now, if the object is in this place, we can draw our force vector. We know it's going to be, I'm not drawing it yet. What is it going to be though? How would we draw this? I'm jumping ahead. So, excellent job. It's a tangent line. Perfect. So it's going to be tangent to the curve. Great work. Okay, so I'm going to call that F with a D. Okay, so it's going to be tangent to the curve. So that whole perpendicular idea, we were just perpendicular to the wrong thing. It's not perpendicular to gravity. It's going to be perpendicular or tangent to the curve. All right, so we have this, and we want to draw the free body diagram by itself. So that's what it would look like. So a lot of repetitiveness. Okay. All right, so this next one, what's some of the wording in here that you really need to pay attention to? So this slides without friction. Because it's sliding, we know that we're in motion. They try to designate that motion by the wind behind the object. Okay. All right. What you got? Excellent. How do we draw it? Straight down. Perfect. Okay. What else? You keep saying that, but it's the normal normal force. How do we draw someone else? How do we draw the normal force? How about my peeps in the back of the room? You guys still with me? Yeah. Yes, perpendicular to the floor, to the surface that we're on. So it's going to look like this. So this is our normal force. This is our gravitational force. And so our free body diagram is just going to look like this. All right, what I would like to do with this problem is kind of get into the whole drawing the components and what that looks like when we have an object in motion, okay? So tell me, guys, I have this ramp here. Is this box falling through the surface? No. Why not? Why wouldn't it fall through the surface? Yes, because the forces are equal, which means my normal force here has to equal some opposing force. All right, so in that direction, the forces need to be equal. But here's the thing, you guys, notice there is no direction, there is no vector that is equal and opposite to the normal force, okay? But the component of a vector is, okay? So what I'm going to do is, because the normal force is the one that we can easily see has to be equal and opposite to a force, I'm going to draw my y so it's in the direction of the normal force. So I'm going to draw this dotted line. There's my y-axis and my imaginary x-axis. Okay. And let's do this. We know we have a gravitational force coming down, and that gravitational force needs to be straight down, so I'm going to draw that first. And the advantage to drawing this is if you have a resultant vector that is not on the x or the y axis, okay, then it's easy to draw the components. So you guys see the end of this tip here, this arrow? Okay. You see how far low it goes? That's the y value that's going to be here. So this is the y component of the gravitational force vector. So FGY. And then our other component is going to be the, not y, but the x component. All right, so I'm looking on this axis how far to the right, kind of like an ordered pair. So literally kind of think about it that way. This is an xy ordered pair. So I'm going to draw an x vector that goes out as far as the tip of this point does. Make sense? So this is F, G, and that's my x component. Good? All right, so here's the thing. You see this y component here for gravity? That is the one that is equal and opposite. So if I try to measure this to make it exact, 1, 2, 3. Okay. So this has to be my normal force, and these two are congruent. Do you see what I mean? So what's happening, you guys, is the sum of the y component vectors cancel out. That keeps the box from sliding through the surface. They're going to cancel out. Okay? So this one's positive, this one's negative, so they're equal to each other. But if you add them, you would have a positive plus a negative equals 0. Then all we have left is the x component. And you guys know what this x component is doing? It's actually making it slide down the ramp. All right, so our net force in the x direction, our net force in the x direction is the x component of the gravity vector. So if I said, hey, what is the value of the force causing my box to slide? I would say, oh, it's, who knows, 5 newtons, right? So my net force in that x direction is 5 newtons, and that's what's pulling the box down and making it slide. So maybe my force due to gravity here, maybe this is like 13 newtons. I wouldn't say 13, even though it's gravity that's making it, but part of this gravity is canceling out the normal force. Do you see what I mean? So if I'm looking at that force vector as a pull, this one's being canceled out with the normal force, and this part of it is making it slide down, but gravity's really working this way. Good? I like how I had it at an angle. Gravity's working this way always. Okay.